Amides are hydrocarbons with amide functional groups. Again, the functional group matches the name of the family. They are almost exactly like esters, except instead of seeing CO C double bonded O, you'll see CN C double bonded O. They only differ by one atom. They have the general formula R, which is your parent chain, CON R prime 2. Because nitrogen can bond to three things, there are two R primes. They do not need to be the same. They can either be hydrogens or carbons. Amides are also classified as carboxylic acid derivatives because they're often made by reacting a carboxylic acid and an amine together. Here's an example. If I react methanoic acid with methanamine, you see the ingredients to make the amide right away. I have a C, an N, a C with a double bonded O. If I use a dehydrating agent, I can remove water from this molecule. Because this C now only has 3 bonds, it will look for something to bond with. And because the N has lost the H, it needs another bond as well. So they will bond together. And that creates my amide functional group. Naming an amide is like naming an ester. The parent chain is the piece with the double bonded O. It does not have to be the longest consecutive chain of carbons. You name this like you would name a carboxylic acid. Then you drop the oic acid suffix and replace it with amide. Make sure to drop the E of the parent chain. Name any other alkyl groups attached to the parent chain as the prefix. Now here's how it differs from esters a little bit. Name the alkyl groups attached to the other side of the nitrogen using N as the position number, and place these in front of the prefix. So this is the same as naming an amine. Here are some examples. Since this is where my double bonded O is, my parent chain consists of 3 carbons. That gives me the root, prop. Because I have single bonds between my carbons, this would be propane. I drop the E and add amide to indicate the amide functional group. Because there are no other carbons attached to the nitrogen or no side chains off of my parent, the molecule's final name is propanamide. This would be an example of a primary amide because my nitrogen is only attached to 1 carbon. Example B. My parent chain would be 2 carbons. It has to be the carbons that are attached to the double bonded O. Because there's 2, my root is going to be eth. Because I've got single bonds between the 2 carbons, and then I would add the suffix amide to indicate the amide functional group. In order to describe the carbon attached to the nitrogen, I would put a methyl out in front with a position number N. Molecule B is N-methyl ethanamide. Pause the video and write the name for molecule C. Here's the answer for molecule C. here's my C double bonded O, so the carbon chain attached to it will be my parent chain. Because it consists of 4 carbons, I get the root bute. There's single bonds between those carbons, so an, and then I use the suffix amide. I then describe any side chains attached to my parent chain. I number it so that the amide gets the lowest possible number. I include a 2-methyl in my name. Finally, I describe the carbons attached to the other side of the nitrogen. I have 2 ethyl groups. Because there are 2 of them, I include the prefix di, and I use the position number N and N. Molecule C final name is NN-diethyl 2-methyl butanamide. Properties of amides. Depending on which classification of amide you have, the melting point and solubility has a range. If you have a primary amide, then your molecule can make 2 hydrogen bonds and 1 dipole-dipole. It makes 2 hydrogen bonds because there's 2 H's directly attached to the N, and the dipole-dipole comes off the C double bonded O. If you have a secondary amide, you can get 1 hydrogen bond and 1 dipole-dipole. If you have a tertiary amide, then your functional group can do 2 dipole-dipoles because now there are no H's directly attached to the nitrogen. Each classification has a higher melting point than a nonpolar alkane. These combinations of intermolecular forces are very strong. That gives amides the characteristics of most of them being solids at room temperature. In terms of solubility in water, again you get a range depending on what classification. If it's primary, you can make 2 hydrogen bonds with water, and you can accept 1 hydrogen bond off of the C double bonded O. For a secondary amide, you can make 1 and accept 1 hydrogen bond. And if it's a tertiary amide, you can accept 2 hydrogen bonds. This combination of intermolecular forces make amides have higher solubilities than alkanes. Other information about alkanes. They are heavily used in the plastic and the rubber industry.